My name is Nicholas Vlachopoulos and I'm in charge of the software group at Automated Analysis Corporation. I have also worked extensively in developing Comet Acoustics, which is the software product used in the numerical examples in this lecture series. What we are going to discuss is the coupled analysis, and by using the term coupled, we mean that we solve the structural vibration and the acoustic response simultaneously. In this manner, we are able to account for the effect of the acoustic medium on the structural vibration, and also at the same time for the effect of the structural vibration on the generated noise. In the overview, we are going to discuss why coupled analysis is important, and then we are going to go over a simple example problem using a 2 degree of freedom system and explain the differences between the coupled and the uncoupled analysis. And finally, we are going to go over the theory section, where we are going to discuss the equations involved in the coupled structural acoustic analysis, and also discuss the procedure by which those equations are being solved numerically. The coupled analysis is useful in 2 cases. First, when we have a strong interaction between the acoustic medium and the structural vibration. And the second case is when we want to solve problems where we have noise transmitted through flexible structures. For example, if we have a plate which is vibrating in the air, the response is going to be very similar if the plate was vibrating in vacuum. However, if we submerge that plate in another acoustic medium like water, then the existence of the acoustic medium is going to affect the vibration, and in that case we need to perform a coupled analysis in order to account for that effect. Also, in cases where we have very strong acoustic excitation, like maybe the engines of a rocket, that very strong acoustic field is going to excite structural components, something like the fairing of the rocket, and we need to be able, in that case, to compute the structural vibration that is getting generated due to the intense acoustic field. Also, in other cases where we want to compute the noise that is getting transmitted through flexible structures, we might have in mind an example of noise generated by an engine and transmitted inside the flexible compartment of a passenger car. So these are just 3 typical example cases where the coupled analysis is important, and we need at the same time to solve for both the structural vibration and the acoustic response. In this tutorial, we are going to use 2 single degree of freedom models and utilize them to explain the differences between coupled and uncoupled analysis. We consider the response of the first model to be the structural vibration, and the response of the second model to be the acoustic response. Typically, we have a structural finite element model representing the structure, and then an acoustic boundary element model representing the acoustic medium. In the uncoupled analysis, we solve first for the structural vibration, and once we have that information, we utilize it as boundary condition for our acoustic analysis, and using the boundary element method, we are able to compute the acoustic response. In the coupled analysis, instead of solving the 2 systems individually, we connect them together, and in that case we solve for the structural vibration and the acoustic response simultaneously, and at that point we are able to account for the effects of the structural vibration on the acoustic response and also for the effect of the acoustic response on the structural vibration. In the uncoupled analysis, the structural vibration and the acoustic response are being computed separately. First, we use the structural finite element method to compute the response of our structural system, and then we use the boundary element method to compute the response of our acoustic system. In this case, we have a single degree of freedom model representing the structure. We have applied a mechanical load as excitation, and we compute the structural vibration by accounting the mechanical load and the mechanical impedance. Then we use the structural vibration that we computed in the first step as boundary condition for our acoustic analysis. In this case, we have a single degree of freedom model representing the acoustic medium, and the response of that single degree of freedom model represents the acoustic response. When we use the boundary element method, we use the structural velocities as boundary condition comprising the excitation in the acoustic analysis, and then we compute the noise at any data recovery point which is generated due to the structural vibration. Again, in this case, we have the equations of the single degree of freedom model that express the acoustic response in terms of the characteristics of the acoustic system, the mass and the stiffness of the single degree of freedom model in this case, and also the acoustic response depends on the boundary conditions imposed from the structural vibration. It is worthwhile to keep in mind these two equations for the structural response and the acoustic response in the case of the uncoupled analysis, and then later compare these expressions with those that we are going to derive for the coupled system. In the coupled analysis, both the structural response and the acoustic response are being computed simultaneously. We are using the two single degree of freedom models that we utilized in the uncoupled analysis, but in this case we have connected them together. And similar to the previous example of the uncoupled analysis, we use as excitation a mechanical load applied on the structural system. Because we have connected the structural system and the acoustic system together, the structural response is going to be influenced by its contact to the acoustic system, and also the acoustic response is going to be influenced by the properties of the structural system. In this simple example problem, we have not included any damping neither for the structure or for the acoustic medium, just so that the derivation of the equations is simplified. This system here represents the coupled equations for this 2 degree of freedom system, and the terms that cause the coupling are these two terms in the first equation due to the physics of the problem. By solving the system of equations, we get an expression for the structural response and for the acoustic response. In a practical application, we would have used a structural finite element representation for the structural system and an acoustic boundary element representation for the acoustic system, and then we would have derived the coupling in that case, as we are going to perform in a little while. But in this simplified case of the 2-degree of freedom system, we have an expression for the structural vibration and the acoustic response, and we can see that the difference between the expression derived from the coupled system of equations and that derived from the uncoupled system of equations is being highlighted with red, and it's achieved through this additional term in the denominator of the two equations. One thing to notice is that the terms in the denominator, all the terms in the denominator include a quantity from the structural system and the acoustic system, except the term which is highlighted, and it represents the coupling effect, and that one includes both terms from the acoustic system. Another thing to point out is that, for instance, in the equation that derives the structural response, if we eliminate the highlighted term, then we can factor out from the denominator the minus omega square ma plus ka, and then eliminate that both from the numerator and the denominator of this expression, and then we are going to end up with the same expression as we had in the uncoupled system. Here we are going to assign some numerical values to the parameters of the structural and the acoustic system, and then carry out the computations in order to compare the results between the uncoupled and the coupled analysis. Specifically, we assign 1000 newtons per meter as structural stiffness and 50 kilograms as mass, and we use as excitation a mechanical force of 20 newtons. For the acoustic system, we use stiffness of 10 newtons per meter and 0.5 kilograms as mass. Something else that we could have done is apply an excitation as well in the acoustic system, maybe something that simulates the speaker that excites the acoustic medium, and then that induces a vibration on the structural system, but that's something that you can try as another numerical example on your own. In this particular case, we are also using 5 rads per second as circular frequency. By utilizing all these numerical values for the parameters included in the equations for the uncoupled system, we are able to come up with numerical values for the structural response and the acoustic response using the uncoupled equations, and also by using the same parameters, the same values for the parameters of the structural and the acoustic system, come up with another set of values for the structural response and the acoustic response utilizing the coupled system of equations. In this particular case, we can notice that the coupled response is greater than the uncoupled. Some numerical examples that you can try on your own is vary the parameters that we utilize for the structural stiffness or the acoustic stiffness, and see what effect that is going to have in the comparison of the results between the uncoupled and the coupled analysis. You can also try for the same set of parameters for the coupled system, you can try to vary the circular frequency and identify the range in which the differences between uncoupled and coupled analysis is important. In the theory section, we are going to discuss how we derive the coupled system of equations and then the numerical procedure that we use to solve the system of equations. We are using the structural finite element method to come up with the matrices representing the structural system, and the boundary element method to come up with the matrix representing the acoustic system. We have the structural physical degrees of freedom as variables for the structural model, and the primary variables on the surface of the boundary element model as unknowns for the acoustic system. We can have as excitation either mechanical forces applied on the structure or acoustic excitation applied within the acoustic medium. The coupling between the two systems is achieved through the diagonal terms in these equations, which represent, the first one represents the effect of the acoustic medium on the structural response, and the second one represents the effect of the structural vibration on the acoustic response. What we are going to discuss here is how we derive the coupling matrices and how we account for the effect of the acoustic medium on the structural vibration and the effect of the structural vibration on the acoustic response. The coupling matrices are derived based on the following principles. For the coupling effect that the acoustic medium has on the structural vibration, we take into account that the acoustic pressure between the two sides of the structure is going to exert a mechanical load on the structure itself. And that can be expressed mathematically, that the pressure difference between the two sides is going to generate a force which is equal to that difference times the unit normal times a differential area on which the pressure is exerted. Also, the effect of the structural vibration on the acoustic response is accounted by expressing mathematically that the acoustic velocity on the boundary element model is directly associated with the structural vibration. And basically, the acoustic velocity is the projection of the structural velocity along the normal on the boundary element model. So by utilizing these two physical principles, we are able to assemble the coupling matrices that we saw before in the coupled structural acoustic system of equations. Although we utilized the physical degrees of freedom for the structural system when we derived the coupled structural acoustic equations, what we are going to do is represent the structural physical degrees of freedom in terms of their model. And we have two reasons for doing that. First, we are going to reduce the number of variables for the structural system, and then we are going to transform the structural matrices into diagonal matrices due to the orthogonality property of the normal modes. So in this case, what we do is we express the structural physical degrees of freedom in terms of the normal modes of the structural system and the model degrees of freedom. For instance, for a structural system that might have 20,000 structural degrees of freedom, we might only utilize 200 modal degrees of freedom to represent the system. So we have a significant reduction in the number of parameters that we use to describe the system. It is also important to mention that we want the normal modes to be mass normalized, but that is probably the default in most computations, in most structural finite element computations, which allows us to compute normal modes. By utilizing the expression of the structural physical degrees of freedom in terms of their model in equation 1, we are able to absorb the modal matrix in the coupled system of equations and transform the coupled matrix to represent the coupling between the acoustic degrees of freedom on the surface of the model with the modal degrees of freedom of the structure. Next, we are going to pre-multiply the structural system of equations with the transpose of the modal matrix in order to utilize the orthogonality property of the normal modes and transform the structural stiffness and mass matrix into diagonal matrices. So for the top part of the coupled system of equations, which represents the structural system, we pre-multiply all the terms with the transpose of the modal matrix. Now we can utilize the orthogonality property of the normal modes to transform the mass and the stiffness of the structural system into diagonal matrices. The mass matrix is going to be transformed into the unit matrix, and the stiffness matrix is going to be transformed into a matrix with non-zero values on the diagonal terms, and those non-zero values are the eigenvalues of the system. One important thing to point out is that we need to have mass normalized eigenvectors so that when we pre-multiply and post-multiply the mass matrix with the modal matrix, we can get the unit matrix. So far, we have utilized the modal matrices in order to transform the physical degrees of freedom for the structure to the corresponding modal degrees of freedom. So instead of having mass and stiffness matrix for the structure, now we have to deal with diagonal matrices. We have transformed the coupling matrix that represents the effect of the acoustic degrees of freedom to the structural degrees of freedom to represent the effect of the acoustic primary variables on the surface of the model to the modal variables of the structural system. And also we have transformed the structural forces to the corresponding modal forces. Next, we are going to use a partitioning and condensation technique to reduce the system of equations to that of the acoustic degrees of freedom. In order to do that, we are going to take the first equation, the top part of the equation of the coupled system, and express the modal participation factors of the structural system in terms of the different matrices and the structural excitation that it is included in the equations, and also in terms of the acoustic primary variables on the surface of our boundary element model. Once we achieve that, then we can substitute that expression into the lower part of the system of equations and come up with a reduced system that has as variables only the primary acoustic variables on the surface of the boundary element model. Something to note here is that because we utilized modal degrees of freedom for the structure, the inversion of this matrix, which is included in the effect of the structure in the acoustic variables, is not at all difficult to do because this is a diagonal matrix, so there is no computation cost associated with inverting a diagonal matrix. In this condensed system of equations from which we compute the primary acoustic variables on the surface of our boundary element model, we can very easily see the effect of the structure in the acoustic system of equations, and also the effect that the structural mechanical load can have in the acoustic response on the surface of the boundary element model. Once we compute the primary variables on the surface of the model from this condensed system, we can do two things. One, be able to compute the acoustic response at any point in space, since we now know all the primary variables on the surface of the model, and we can go back in the expression that we obtained for the modal participation factors in terms of the primary acoustic variables on the surface of the model, and back calculate the modal participation factors, that is information about the response of the structural system. Then we can go one step further back and actually derive the physical degrees of freedom for the structure from its modal participation factors. And that the computation of the primary variables on the surface of the model and the computation of the structural behavior concludes the computations for the coupled structural acoustic system of equations. Before we conclude the lecture on the coupled structural acoustic analysis, it is important to point out the capability of having an unequal mass density between the acoustic model, the acoustic boundary element model, and the structural finite element model. We utilize an acoustic boundary element model to model the acoustic medium, and then a structural finite element model to represent our structure. In most practical applications, the discretization in the structural finite element model is much finer than that of the acoustic boundary element model. And that can be handled in the coupled analysis by assembling appropriately the coupling matrices that account for the effect of the acoustic medium on the structural response and the effect of the structural vibration on the acoustic response. Further, it is possible to identify only a certain portion of our boundary element model to be interfacing with a structure. And we can have another portion of our acoustic boundary element model which we do not consider to be interfacing with the structure. Similar, for the structural finite element model, we can assign only a portion of it to to be interfacing with the acoustic medium and have another portion of our structural model not associated with the acoustic boundary element model. In addition, we can include modal damping in the system of equations for the structure, and that's something that was omitted in the derivation of the equations in order to keep the derivation simplified. And also we can account for absorption in the acoustic boundary element model by assigning some complex speed of sound for the acoustic medium.